Hello, I'm Alex. I'm a DPhil student at the Department of Engineering in Oxford. Welcome to our presentation, Slice-to-Volume Registration Enables Automated Pancreas MRI Quantification in UK Biobank, that I did in collaboration with Perspectum. I would like to thank MIUA and the organizers for the opportunity to present our work. Multiparametric MRI of the pancreas is becoming important for diseases like type 2 diabetes, pancreatitis, or pancreatic cancer. Multiple MRI biomarkers for the pancreas have been developed, for instance, pancreas volume, fiber inflammation, fat, or pancreatic duct characterization. Disease characterization can sometimes benefit from image fusion between acquisitions. The UK Biobank study plans to scan 100,000 volunteers using an abdominal multiparametric protocol that includes the pancreas. Previous work on UK Biobank have used the pancreas segmentation from a volumetric scan to extract a region of interest, ROI, on a 2D quantitative map from a different scan, acquired during a separate breath hold. The small and irregular structure of the pancreas means that only small differences between breath holds can cause poor organ alignment between scans, which in turn leads to quantification errors when using this approach. In this work, we propose slice-to-volume registration with multimodal similarity for aligning these two scans and producing accurate T1 quantification downstream. For this work, we used two scans from UK Biobank. The first is a pancreas-specific volumetric scan, for which we had available 3D automated pancreas segmentations from segmentation work that we presented last year. We also used a quantitative 2D T1 map derived from the shortened MOLI scan. 14,439 subjects with both scans available were processed using no registration and our slice-to-volume registration method. We observed empirically that misalignments in the transverse direction are the most prevalent in our data. For this reason, our method proceeds with an initial alignment in the axial plane and then performs exhaustive rigid search along the transverse direction. We explored two different similarity metrics, one using normalized mutual information, the other using self-similarity context descriptors. These yielded two slice-to-volume registration methods that we tried, that we refer to as SVR-NMI and SVR-SSC. For the alignment in the Z direction, the volumetric scan and its segmentation are first resampled into slices along the Z direction. Because the T1 slices are oblique and the volumetric scan had limited coverage, we sometimes experience missing data at the extrema. We will come back to these in the discussion. We then compute image similarity between the resampled volume slices and the 2D quantitative T1 map, shown here. We then chose as our optimal Z translation the one that gave the highest similarity between scans, or lowest cost. We then chose the resampled segmentation at that chosen location as the pancreas segmentation for the T1 map. Here is an example applying no registration at the top, which is based on the DICOM header positions for alignment, and applying SVR-SSC at the bottom. The optimally determined translation in this case was 10 millimeters. We performed quality control of the data. We first excluded subjects with empty output 2D pancreas masks. This was mostly due to empty automated 3D segmentations upstream. For the remaining subjects, we also excluded based on mask size, initial overlap of the two scans, and T1 slices with non-axial orientations. Here you can see an example of an excluded slice that had coronal orientation. We also excluded subjects where the suggested translation by the registration was greater than 10 millimeters. These ensured enough overlap between the two scans, but we'll come to this issue later. We performed two validation experiments for our method. The first was a direct validation of the alignment error between methods using annotated manual reference positions, whereas the indirect validation used output segmentation quality, using manual delineations that had been performed on the T1 slice directly as reference. We used dice overlap and 95% Hausdorff distance as metrics. Here are the results for the T1 quantification differences between no registration and SVR-SSC. The small bias at 1.4 milliseconds suggests we may be able to use either of the methods at the population level, for instance to report the median T1 for the population. For individual subjects, however, registration may be required, since the variability of 53 milliseconds yields the two methods not equivalent. Here are the results for the technical validation. For the direct validation, here is a comparison of the error for all three methods on those 50 subjects with annotated reference positions. The alignment error was significantly reduced when using any of the two slice-to-volume registration methods. The difference in alignment error between methods was not significant. Similarly, for the indirect validation, the segmentation overlap with reference annotations improved using any of the two SVR methods. The difference between methods was not significant, though SVR-SSC appeared more robust to challenging examples. You may find the plots for the indirect validation as well as the challenging example on the paper. This work has some limitations. The moving image, which was the 3D scan, had limited coverage. This meant that the search range over the transfer direction was limited, which sometimes affected convergence of our method to the correct solution. Using the whole body scans would extend this range, though these have lower resolution and are more difficult to segment. Local deformations or through-plane deformations were not considered, which are prevalent in abdominal breath hole scans. The performance of our method using affine and rigid alignments encourages more advanced approaches. Also, the 39% exclusion during QC could have biased the results, though this was due mostly by failure of the upstream segmentation method. In conclusion, slice-to-volume registration enables automated pancreas segmentation and improves quantification in multiparametric MRI protocols. SVR improved T1 segmentation quality, as well as pancreas T1 quantification for an individual in UK Biobank. Our method is compatible with other 3D and 2D image types on UK Biobank, for instance the 3D whole body scans or 2D quantitative PDFF maps. Thank you for your attention. I'll be happy to answer any questions.